Video recording, we are going to talk about aldol addition reactions and aldol condensation reactions. Okay, talk about aldol reactions. This is actually a continuation of the enolate chemistry. So once you have understood chapter 22, which talks about enolates and its formation, this is continuation of that chapter. Okay, but it's actually discussed in chapter 23 in our textbook. Okay. All right. So if you remember when we were discussing the types of bases that can be used to deprotonate, deprotonate to form the enolate ion, we had discussed that if you use a um, strong base like sodium hydride or LDA, then this reaction goes to um, forward direction completely, where the enolate is formed as the product. Okay, because this is a base, it will abstract this alpha protons because of its acidic nature, and you can form an enolate like this. Okay, however, if you take this same aldehyde and treat it with a weaker base like sodium hydroxide, then it is an equilibrium reaction where you will get the enolate and the starting material in an equilibrium. Okay, that means because it's not a strong base, it will not form the enolate completely. It will do a reaction where part of the starting material is converted to enolate, but we also have a large amount of the original starting material left. Okay, so this is what is the condition for the formation of an aldol. So since the once we form the aldol, so for example, for formation of an aldol, we need two molecules of this. Okay, so we will take this, form the enolate, and then that enolate is going to react with one more molecule of this to give you a aldol product. Okay, so this is the final product that will be formed. So if you see, we have combined these two aldehydes to form what is called as an aldol. Okay, so put the equilibrium arrow, and then the conditions that we need is sodium hydroxide followed by hydrolysis. Okay, so if this is the reaction which is called as the aldol addition reaction. We'll look at the mechanism in a minute. Okay, let's look at the mechanism. Of aldol reaction. Okay, aldol reaction. So let's take the simple aldehyde where we have alpha hydrogens only at one of the carbon atoms. Okay, so that means since it's an aldehyde, we do not have any alpha hydrogens here, but we do have alpha hydrogens here. Okay, so we have taken CH3CHO, which is acetaldehyde, and using a base. Now remember, we have to use the two arrows here to show equilibrium. So since we are using a weaker base like sodium hydroxide, this is going to abstract one of the protons and then form the enolate at this point. Okay, so we have H double bond O, and then I have the enolate formed. Now, since this reaction will also have my starting material, right? So this enolate is going to react with the starting material. Okay, so let's put down the starting material here. H O CH3. Okay, this is my starting material. So my enolate is now going to act as a nucleophile, and it's going to attack the carbon atom which is having the carbonyl group. Okay, and putting the electrons here. So it's kind of a addition reaction, right? So you are extending the carbon chain, and then you get a intermediate, because we have this double bond O, and let's call these carbons as or put a color over there, or call them as A, B, and C. So let's call this as A, and then this is B. Okay, so just keep it A and B so that we can track the carbon atoms, right? Um, so this was my A, and then see it forms a bond to B, and then the oxygen is now negatively charged, right? Then you have the CH3 group here. Okay, so this was my A carbon atom, this is my B carbon atom. Okay, so you have extended the chain, but now the last step would be where you have the hydrolysis. The oxygen takes the proton from here and becomes the aldol product. This is my aldol product. So every time when you draw an aldol, make sure that the at the beta position you have a hydroxy group, right? So this is my alpha position, and this is my beta position. So at the beta position we have a hydroxy group, so this is also called as a beta hydroxy um, compound. Okay, so this is one of the examples of a aldol reaction. Many of the ketones, they generally do not form this aldol product. The equilibrium is usually towards the starting material. We don't get much of the aldol product, but aldehydes, like smaller aldehydes like this, they tend to give us the aldol product. Okay, it's a very nice reaction, and this is what you're going to be doing in the lab this week, where you will be given two of the carbonyl compounds, maybe two different aldehydes, and then you are going to combine them to form the aldol product. Okay, um, let's look at one more example. Okay, so sometimes the question may be asked that how, or you can draw the aldol addition product for the following carbonyl compound. Okay, for the following. Okay, it could be a ketone, it could be an aldehyde. So here I'm taking an example of a aldehyde. Okay, I have an example of an aldehyde here. Now you're asked to draw the aldol addition product. So that means you can do the whole mechanism like this. So the first step is identifying the alpha hydrogen atoms, because first step is the formation of the enolate, right? So I'm going to just turn this around like this to make sure that my alpha carbons are more clearly seen. So this is my alpha carbon, and these are the hydrogens, alpha hydrogens, right? So the first step again is using a weak base, okay, because if you use a strong base, the reaction will go to completion, where it will, all of the starting material will change into an enolate, but we don't want that to happen, because we want the enolate created to react with the starting material again, right? So we use a weaker base. So drawing the arrow, this forms the enolate. So we have H double bond O is here, and the enolate is formed here. Okay, now remember, this enolate is going to attack the starting material, right? So again, it will be a good idea for us to label them. So I'm going to call this as A, and then this is going to react with my starting material H O, this, right? This is my starting material. So the enolate is going to go ahead and attack this carbon atom, which I will label it as B. Okay, which I'll label it as B. So you know that the bond is formed between A and B. Okay, so that is why it is a good to keep track of the carbon atoms. It's a good idea to label them, right? Okay, now the product. Let's just combine them. Make equilibrium arrow. So we have H double bond O, and then this. Okay, so now I'm going to connect A and B. So this was my A, and this is B. Now this goes over here. So I have an O negative charge, right? And then what else is connected? At A, see, you still have this alkyl group, right? So need to make sure that I have it there. And at B, see, again you have this R group sticking there, right? So this will be my intermediate, and then finally removal or protonation step. You are finally protonating it to form your final product, which is H double bond O, OH here, R groups that are hanging in, right? So don't miss these. So that's why I feel like labeling them helps, because you know that A and B is the bond that is formed, and it is the beta hydroxy carbonyl compound. Okay, so see, this is my alpha position. At the beta position, you have a hydroxy group. So this is my final aldol product. Okay, so make sure you practice a few more reactions involving aldol reactions. Now, there is a additional reaction that can happen, and that is aldol condensation. Okay? So generally this aldol addition may not be that favorable, but aldol condensation is. Okay? So aldol condensation, and what do we mean by that is, if once the aldol product is formed, then under acidic or basic condition, it can undergo an elimination reaction to produce unsaturation, okay, alpha beta unsaturated compounds. So if you have an aldol, okay, so once you form the aldol by the normal mechanism that we saw before, then if you so say for example I have an aldol like this, okay, see at the beta position I have an OH, then in the presence of a acid or a base, okay, acid or a base, and heat is generally favored, it can undergo an alpha beta or it can form an alpha beta unsaturation here by removal of a water molecule. So you can think that an OH from here and a hydrogen from here is removed, and that you end up with the formation of an alpha beta unsaturated compound, alpha beta unsaturated product. Okay, see, this is my alpha position, this is my beta position, and you created an unsaturation, so this is called as an alpha beta unsaturated product, and the side and the water molecule is eliminated. Okay, so this condensation is really very highly favored. You don't have to put the two arrows because it's all driven to the formation of this unsaturation. See, there is a conjugation, right? So that is also a favored process. You recall from chapter 14, conjugated compounds are stable. So you can see that there is a double bond here, single bond here, double bond here. So the formation of a conjugate compound is favored, and therefore aldol condensation happens pretty easily. Okay. All right. So I would expect you to know what is an aldol reaction and what is an aldol condensation reaction. We will talk about Claisen condensation in the next video, but make sure you also practice a few of the crossed aldol. Okay, so crossed aldol means where you can take two different carbonyl compounds and combine them to form the aldol. So right now, if you look, we had taken only one carbonyl and it formed the enolate and it reacted back with the same compound, right? But we can have crossed aldol. Okay, so for example, let me give you one example before we end this video. So in a crossed aldol, so for example, if I take a formaldehyde and then I treat it with another aldehyde. Okay, so two different aldehydes. So see, this one does not have any alpha hydrogen atoms, so this is the one that will form the enolate. Okay, so let's write down the mechanism here. So I'm going to again turn it around like this to expose the alpha hydrogen atoms, and then so first step would be treatment with OH minus to form the enolate. Okay, so I form the enolate here. And now this enolate will react with the other aldehyde. Okay, so we can react it with the other aldehyde, which is my formaldehyde. Okay, so again, this is this the enolate is going to attack over here. This goes over here. So what do I get? H double bond O. This one, and I have the R group. See, this R group has to stay here because the bond is formed to the other carbonyl carbon. This oxygen gets a negative charge. I just have a hydrogen here, right? Because there are two hydrogens, so I can just put the two hydrogens here. Now the last step would be, these are all equilibrium metals, would be hydrolysis, where this propionation happens, the formation of a beta hydroxy compound. Okay, so I don't need to draw that. Hydrogens, not necessary to draw the hydrogens. To keep my R group here, right? This R group. So this will be my product. Okay. Yeah, this will be my product. So I have the beta hydroxy um, carbonyl compound. Okay, so see, this is at the beta position. I have a hydroxy. You can keep the hydrogens if it is confusing. Okay, but that is my product here. So this is be an example of a crossed aldol because I'm treating two different or reacting two different aldehydes. Okay, one was a formaldehyde and this was a propionaldehyde. Okay, so we have 1, 2, 3. So it's propionaldehyde. All right, so we'll talk about more condensation reaction in the next video, but this I wanted to post before you take the lab, you do the lab, so make sure you watch this before coming to lab this week.